we are going to have the second talk in Vienna. Maybe we can come back to the Vienna main screen. Can we? All right, we can. We can't hear you. Yes, we can hear you. Thank you. So I assume we are going to listen to Matthias Horn, correct? Or maybe Günther Raidl. I can't see you from there.
Yes, Matthias Horn.
All right. Thank you, Matthias. So we are going to hear about relaxed decision diagram again. Well, decision diagram again, and you have 15 minutes. Can I ask someone in Vienna just to check the time, because I'm not sure it's feasible to do that remotely?
Yes.
Thank you.
Okay, so welcome to my presentation. As already clarified, I'm Matthias Horn, and this is a joint work with Günther Raidl, and today I want to talk about the star-based compilation of relaxed decision diagrams for the longest common subsequence problem. And as the title already reveals, we want to compile relaxed decision diagrams. So they are relaxed decision diagrams provide a discrete relaxation of the solution space of the common dual optimization problem. And we in this work mainly use them to obtain dual bounds, but in the last decade, they were successfully applied on many standards optimization problems in different ways. And recently we published a novel star-based construction algorithm to compile relaxed decision diagrams. And we could show with this algorithm that we can obtain smaller decision diagrams, which provide stronger relaxations. And we can do this in shorter time than to compile relaxed decision diagrams with traditional methods from the literature. However, we demonstrated this on a new price collecting scheduling problem. So in this talk, we want to apply it on the longest common subsequence problem. So we want to compile relaxed decision diagrams for the longest common subsequence problem, which is a more prominent problem and is also deeply investigated in the literature. I want to show that we are able also to compile relaxed decision diagrams that provide better upper bounds than the current state of the art upper bounds from the literature. Okay, so what is the common subsequence problem? For this problem, we have given m input strings, which are defined over a finite alphabets sigma, and we want to find the longest common subsequence. So what is a subsequence? A subsequence is a string that can be derived from an input string by deleting 0 or more characters from it. And a common subsequence is a subsequence which can be derived from all input strings. So in this example here, in this small example with 3 input strings, we see that the common subsequence BDABC is indeed a common subsequence because we can derive it from all 3 input strings. And in this example, this subsequence is also a longest common subsequence. Okay, the LCS problem has a wide range of applications. One of its most important fields is in computational biology, where strings usually represent any or DNA segments. And as I already said, it's a deeply investigated problem. There exists exact as well as heuristic approaches. And if the number of input strings is fixed, then there exists dynamic programming formulation which can efficiently solve the problem in polynomial time. However, if the number is not fixed, then the problem is NP hard. And for larger instance sizes, we have to apply heuristic approaches. And there are also plenty of heuristic approaches devised as well over the last decades. They range from greedy heuristics over large neighborhood search to wing search methods. And currently, state-of-the-art results can be obtained from an A star-based anytime algorithm, which was suggested by Djukanovic. There are also fast to calculate upper bounds available for this kind of problem. We use these upper bounds to guide our compilation process for the relaxed decision diagrams. So I want to briefly describe them here. The first upper bound was suggested by Fraser and later improved by Bloom and others and is based on the number of occurrences of each character. The second upper bound is based on dynamic programming. So we select here a set of pairs of input strings and compute the longest common subsequence between them. So for 2 input strings, we can do this efficiently in polynomial time. And the third upper bound is actually a contribution by our own, but because of the lack of time, I don't want to talk about the details of this upper bound. Just let me say that it's similar to the second upper bound, so it's also based on dynamic programming, but we select the pairs of input strings in a different way. And the best upper bound which we can use is a combination of all 3 upper bounds by taking the minimum of it. Okay, now, so decision diagram in the context of the LCS problems, here defined as a directed acyclic multigraph. We have a root node, and each arc is associated with a character from our alphabet sigma. And a path originating from the root node identifies a common subsequence. To compile a decision diagram in a systematic way, we associate each node with a position vector. So a position vector contains for each input string the start position of the remaining substring, which we still have to consider. So we can say that the position vector represents a subproblem, which we still have to consider further. And of course, if the decision diagram encodes precisely the set of feasible common subsequence, then we have an exact decision diagram. But however, this problem is NP hard, so exact decision diagram will tend to grow exponentially in size. And therefore, we consider relaxed decision diagrams. So this means that we select subsets of nodes and replace them by a merged node and redirecting all incoming outgoing arcs from it. And the position vector of such a merged node can be computed by taking the minimum of the corresponding position vectors. Okay. Now, a traditional method to compile such relaxed decision diagrams is the top-down construction method. Here, the principle is that we can compile the decision diagram layer by layer, starting with the root node, and each layer is, and the size of each layer is controlled by a maximum width, which we call here beta. And if the current layer exceeds this maximum width, then we start to rank all nodes according to a heuristic function. In our case, we use this fast to calculate upper bound function for the LCS problem, and then we merge the worst ranked nodes. Yeah, there are some advantages of this method. For instance, it's simple and we can easily control the size of the relaxed decision diagram with this maximum width. However, there are also disadvantages. So for instance, states can only be merged within the same layer. And there may be nodes at different layers which correspond to the same states. So we have here some redundancy in the relaxed decision diagram. And there can be also isomorphic substructures in the relaxed decision diagram by this approach because of this layered structure. And to overcome this, we switch now to best first compilation by using a modified A-star algorithm. So in this scenario, layers will not play a role anymore, and we will avoid multiple nodes for identical states in a natural way. And as a consequence, we will also avoid multiple copies of isomorphic substructures. And another key characteristic of this approach is that the expansion and the selection of nodes is guided by an auxiliary upper bound function. Okay, so what is the classical A-star algorithm? It's actually a well-known informed search algorithm for path planning in the field of artificial intelligence. It uses a heuristic function, in our case, the upper bound function, to guide the search, and it maintains an open list of nodes. And this open list is sorted according to a periodic function f, which consists of two terms. The first term here is always the length of the longest path from the root node to the current node u. And the second term is an upper bound on the remaining length. And the algorithm works as follows. So first we initialize the open list with the root node, and then at each iteration we pop the most promising node from the open list. If this node is selected node is a target node, so a target node means that that's a node that we cannot further expand, then we know from the principles of the star search algorithm that the longest path between the root node and this target node must be an optimal solution. We must encode an optimal solution, and we can terminate. And otherwise, we expand this node and insert all created successor nodes into the open list. Now, to compile a relaxed decision diagram, we add here additional steps. So the key idea is that we limit the size of the open list by a threshold value phi. And as soon and after we expand the node, we check if the size of the open list exceeds this parameter phi. And as soon as this is the case, we select nodes from the open list and merge them. So in this way, we don't have to use any layers. We can just merge the nodes from the open list. And now, if we select the target node for the first time, then the length between the longest path from the root node and the target node is a feasible upper bound. And if we're just interested in an upper bound, then we can terminate at this point. However, if we want to compile a complete relaxed edit, then we have to continue the compilation process until the open list gets empty. Okay, so as I said, as soon as we exceed the size of the open list by this threshold value 5, we start to merge nodes from the open list. And we do this efficiently by using a labeling function L. So the idea is that we label all nodes, and if two nodes have the same label, then we consider them as similar and they may be promising to merge. So we only merge nodes which are unexpanded and that has the same label. And to do this efficiently, we iterate one time over the open list, starting with the worst ranked nodes by using a dictionary which is indexed by the open list. And as soon as we find two nodes with the same label, we remove them from the open list, create a merged node, and insert them again in the open list. The domain size of this labeling function has an impact on the compilation time and on the quality of the RelaxDD. So if we choose a labeling function which has a large domain size, then this means that there are many nodes with different labels. So it may be hard to find two nodes with the same label, which we can merge. This results in longer compilation time, but the quality of the RelaxDD may be better. If we choose a labeling function with a smaller domain size, then we will find more nodes which we can merge. So we will be faster compile a RelaxDD, but the quality may be worse of the RelaxDD. Okay, for the LCS problem, we use two different kinds of labeling function. The first one is a static kind of labeling function where the idea is that we select one pair of input string, and we only merge nodes when these input strings have the same position in our position vectors. So this has, as a consequence, the paths now from the root node will encode a feasible common subsequence with respect to these two input strings, but not necessarily with respect to all input strings. And the upper bound of the RelaxDD cannot be worse than the longest common subsequence between these two input strings. And we select this pair of input strings by minimizing this first fast to calculate upper bound function. The second labeling function we use is a dynamic one, where the idea is that we do not only consider two input strings, but four input strings. However, in practice, it turns out that for four input strings, the domain size of the labeling function is already too large, so we cannot compile a relaxed decision diagram in reasonable time. And that's why we discretize the last two values of this labeling function. So we introduce here this discretization factor delta, and we produce in a dynamic way during the compilation process. So we start with a delta of 1, which means that we do not discretize at all. And as soon as we fail k consecutive times to reduce the open list size below 5, we double the size of delta. This means that we decrease the domain size and we will find more nodes which we can merge. And as soon as we can successfully reduce the size of the open list, we reset delta to 1. Okay, now for our experimental results, we use 6 different benchmark sets from the literature. They have different characteristics. So we consider here input string lengths between 100 and 5,000. We consider between 10 and 200 input strings. And we also consider alphabet sizes between 2 and 100. So now the first results I want to show you here are average results of compiled relaxed decision diagrams with the star-based approach and the top-down based approach. We compiled them for different values of phi and beta. And the first diagram shows always the obtained upper bounds. The second diagram in the middle shows the corresponding compilation time. And the diagram on the left, on the right, shows the number of nodes we created during the compilation process. And if we now consider here this brown line, so these are the relaxed decision diagrams which we obtain from the top-down construction method, then we see that we produce here worse upper bounds than with the relaxed decision diagrams which are computed with our star-based algorithm. However, we see here also the advantage of the top-down construction algorithm, because the size of the relaxed decision diagrams are linear with the maximum width, and also the compilation times grow almost linear. This we cannot say about the star-based compilation algorithm, because the classically star-based classically star search algorithm has also a worst case complexity, which is exponential. And this is also true if we compile a relaxed decision diagram with a star. However, we see in practice that in particular for large values of phi, we can compile a relaxed decision diagram faster than with the top-down construction method. If we consider this dynamic labeling function, then we see that we can here in this scenario produce the relaxed decision diagrams with the strongest upper bounds. And if we consider the static labeling function, then we produce relaxed decision diagrams with worse upper bounds, but with the fastest method. Yeah. Okay, then we see here the relative differences between the upper bounds which we obtain from our relaxed decision diagrams and this fast to calculate upper bounds, which are grouped by the benchmark instance sets. And here we see that we have a median relative difference of about 10%. And on the right, we see the relative differences between the upper bounds which we obtain from the top-down construction method and from the star-based construction method. And here we have, for almost every benchmark set, a relative difference of about 50%. Okay, and finally, we compared our obtained upper bounds with the state-of-the-art upper bounds from the literature. And here we see that we can obtain in 25% of the cases stronger upper bounds, and in 35% of the cases stronger or equally strong upper bounds. Okay, so to conclude the talk, we compiled relaxed decision diagrams with a modified star algorithm for the LCS problem. We considered a novel dynamic labeling function, and we observed that we can obtain stronger or equally stronger upper bounds in 31% of the cases compared to the state-of-the-art upper bounds. And a promising future work direction may be to embed this A-star algorithm to compile a decision diagram with the A-star algorithm and embed this in a branch and bound algorithm. Yeah, so thank you for your attention.
Thank you. So do we have questions?
We'll take a live question.
Oh, sorry. There is another question in Vienna?
Yes, there is one.
All right, then we may start with this one.
Let me grab the microphone. So thank you very much for the very interesting talk. This is quite a sophisticated methods and very impressive. I was curious, like, if I understood correctly, you are doing all of this to achieve very good upper bounds.
Yes.
And I would be curious about the impact to solving the overall problem in it, right? Because like did you evaluate what is the impact of your upper bounds on a solution method for the overall problem? How much time can you save or compared to other techniques that do not use the bound?
No, we did not such experiments, but that would be one of the next steps to embed this in a branch and bound framework.
This was the future. Yes. Okay. Because this would be interesting. I guess you have a lot of improvements for this. Yeah. That would be interesting to see this.
I think also this would be interesting.
Thanks.
We have one question in the chat. So the question is, one of the key ideas of your approach is to merge nodes across layers. Is this idea applicable to each problem represented as a DD, or are there any structural assumptions needed?
I think it's not applicable for all problems. You have to be careful if you merge nodes that you don't introduce cycles in the relaxed decision diagrams. So there may be problems where you where you have to use layers to ensure that there are no cycles. But if you can model your problem in some way that you have a state where one dimension of the state always increase if you expand the node, then it's possible.
Okay, thank you. So that answers Michael Romer, and he also says thank you. So we are running out of time, so I suggest we stop the questions for now and go to next talk.